Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the ideal reheat Rankine cycle. We noted in Project 11.4 that increasing the boiler pressure increases the thermal efficiency of the Rankine cycle, but it also increases the moisture content of the steam to unacceptable levels, as shown in Figure 11.7. Then it is natural to ask the following question. How can we take advantage of the increased efficiencies at high boiler pressures without facing the problem of excessive moisture and the final stage of the turbine? Two possibilities may occur to our mind. 1. Superheat the steam to very high temperatures before it enters the turbine. This would be the desirable solution since the average temperature at which heat is added would also increase, thus increasing the cycle efficiency. This is not a viable solution. However, since it requires raising the steam temperature to meteorologically unsafe levels. 2. Expand the steam in the turbine in two stages and reheat it in between. In other words, modify the simple ideal cycle with a reheat process. Reheating is a practical solution to the excessive moisture problem in turbines, and it is commonly used in modern steam power plants. The reheat cycle was introduced in the mid-1920s, but it was abandoned in the 1930s because of the operational difficulties. The steady increase in boiler pressures over the years made it necessary to reintroduce single reheat in the late 1940s and double reheat in the early 1950s. The TS diagram of the ideal reheat Rankine cycle and the schematic of the power plant operating on this cycle are shown in Figure 11.10. The ideal reheat Rankine cycle differs from the simple ideal Rankine cycle in that the expansion process takes place in two stages. In the first stage, steam is expanded isentropically to an intermediate pressure and sent back to the boiler, where it is reheated at constant pressure, usually to the inlet temperature at the first turbine stage. Steam then expands isentropically in the second stage to the condenser pressure. Thus, the total heat input and the total turbine work output for a reheat cycle become. The incorporation of the single reheat in a modern power plant improves the cycle efficiency by 4 to 7% by increasing the average temperature at which heat is transferred to the steam. The average temperature during the reheat process can be increased by increasing the number of expansion and reheat stages. As the number of stages is increased, the expansion and reheat process approaches an isothermal process at the maximum temperature, as shown in the figure. The use of more than 2 reheat stages, however, is not practical. The theoretical improvement in efficiency from the second reheat is about half of that which results from a single reheat. The reheat temperatures are very close or equal to the turbine inlet temperature. The optimum reheat pressure is about 1/4 of the maximum cycle pressure. For example, the optimum reheat pressure for a cycle with a boiler pressure of 12 megapascal is about 3 megapascal. If the turbine inlet pressure is not high enough, double reheat would result in superheated exhaust. This is undesirable, and it would cause the average temperature for heat rejection to increase and thus the cycle efficiency to decrease. Therefore, double reheat is used only on supercritical pressure power plants. A third reheat stage would increase the cycle efficiency by about half of the improvement attained by the second reheat. This gain is too small to justify the added cost and complexity. Remember that the sole purpose of the reheat cycle is to reduce the moisture content of the steam at the final stages of the expansion process. If we had materials that could withstand sufficiently high temperature, there would be no need for the reheat cycle. Okay, that's all for this task. Thank you very much, and see you next time.